Good evening to all the participants. Welcome to an online lecture series on research scopes in emerging areas of civil engineering. So the day 3 lecture is Dynamic Analysis of Functional Guided Materials and its Application. Myself, Dr. S. Pachepan, Assistant Professor, Department of Civil Engineering, Aditya University. So if you see the topic, it comprises of three components. One is the dynamic analysis, functional guided materials, and its application. So before getting into the research topics and its research scopes, it's essential to understand the basics of structural dynamics. So my presentation comprises of two parts. One is the basics of structural dynamics and another part is research. So in basics of structural dynamics, we are going to uh, study about the introduction part and then various classification of dynamic analysis and what is mean by degree of freedom and vibration of single degree of freedom system and multi-degree of freedom system. And for the equation of motion, how to derive the solution. For that, many methods are there that we are going to discuss. And then we are going to discuss the vibration system. In that, many categories are there, undamped, damped, low, so and so, that we are going to discuss. And then finally, summary. And if you see the research part, we are going to discuss about the offshore structures. The reason is offshore structures are subjected to 3 to 4 dynamic loads. For example, wave loads, wind loads, hydrocarbon fire and explosion, impact loads, and also ice loads. So that's the reason, for example, I have took this offshore structure and this is my research work also. Then we are going to discuss about the functional graded materials, how to design the offshore structures, wind load analysis, blast load analysis, offshore structures under impact load. And by considering all these combination, if all these combination of loads are acting to the offshore structures, then what is the consequences that we are going to discuss. And then free vibration analysis of structural members, which is made of FGM. And conclusion, novelty of this research work. And then the take home is a research scopes. So coming to this basic structural dynamics, if you see any structure in the world, it's complex in nature. So structure is made complex because of the loading conditions, particularly the dynamic loads, for example, earthquake load, wind load, wave load, impact load, hydrocarbon fire and explosion, ice loads, all these are dynamics in nature. So when the dynamics loads are acting into the structure, the behavior or the response is different. So it is important to know the response of the structure before going for a design. So here we are going to discuss two different mathematical formulations. One is a lumped mass system, another one is a continuous system. So the lumped mass system means whatever you are seeing here is a water tank. So this water tank is comprises of the post, that is a column. On the top of that, it is having the mass. So lumped mass system means we are going to consider the column mass is negligible. And we are going to only consider the mass on the top of the column. That is a water tank tub which is filled with the water. Now, if this system, the structure is vibrated during the earthquake, it is considered as a single degree of freedom because the displacement produced in all the direction, when it is swaying, it's same in all the directions. So it is considered as a single degree of freedom. Now we'll see what is multi-degree of freedom. So when we are having a multi-story building, here we can able to see G plus 1 story idealization of the building. So here we have the mass 1 and mass 2. So mass is lumped at the floor level. And then the mass 1 at the location mass 1, it is going to produce the displacement 1. And the location 2, mass 2, it is going to provide the displacement 2. So it is considered as a 2 degree of freedom. So degree of freedom means number of independent coordinates required to specify the motion of the system. That we'll see in the upcoming slides. Now another category is the continuous system. But in general, the practical scenario, all the structures are continuous system only. Then why we are going for a lumped mass system? In order to simplify the mathematical equations. Okay, so once a system is considered as a lumped mass system, it is easy to solve mathematically so that we'll be getting the responses. So we can able to solve the continuous system also, but the complex mathematics is involved. So in the, for example, I have taken the chimney here, industrial chimney. The mass is distributed along the height of the structure. So we cannot able to lump the mass here, and the equation becomes very complex here. So these dynamic analyses are broadly classified according to the force, according to the material, and according to the deformation. We'll see one by one. According to the force, according to the force, the analysis is classified into static analysis and then dynamic analysis. Static analysis means the load is static. The load is not function of time. So load is not going to vary with respect to time. For example, dead load, live load, and imposed load, superimposed load, all these structures, all these constant. It's not going to vary with respect to time. So here we can able to see the cantilever beam subjected to point load at the free end. What would be the deflection of this cantilever beam? That deflection also is constant. It is not going to change under the action of that particular load. Now, if you to come into the dynamic analysis, the load will vary with respect to time. So here you see, as long as the force is constant, then the response of the structure is also constant. If you see the dynamic analysis, same cantilever beam only is there, but the applied force P is the function of time. So obviously what will happen? I'm having the cantilever beam, the point load at the free end. If it is a static load, it produces the deflection like this. But if it is a dynamic load, the deflection will be, the position of the beam will be moving in an upward and downward direction continuously. So the deflection also is dynamic in nature. So you see the load history of this dynamic load, it is random in nature. Here also two categories are there. Random load is there, and then deterministic loading and deterministic loading, periodic loading, and then random load. So if you see here, it is not a periodic loading. The load is random in nature. Then what is the example for periodic loading? Some sine loading, sine function, cosine function. In that shapes are considered as a periodic loading. That means the load pattern repeats after some time interval. But here you see the load is completely random in nature. So the response also is the random in nature. Now, classification of materials according to the classification of analysis according to the material. So here, if the loads are within the elastic limit, that is called as a linear analysis. If the loads are not within the limit, elastic limit, then it is called as a non-linear analysis. We'll say Hooke's law. Hooke's law means stress is proportional to strain up to the elastic limit. And if the material behaves elastically, the method of superposition is applicable. Okay. So what is the method of superposition? We'll see by having some example. First of all, whatever the graph you are seeing here is the load versus displacement. Here you can see the straight line because the load, the material nonlinearity is not there here. The material behaves elastically. This load and deformation is proportional. Now coming to the another case, for example, what is meant by superposition? I have a cantilever beam having 1 kilonewton at the free end. So because of this load, the produced deflection is, we'll say A. Now the same cross section, same length of the beam I'm taking, but the load applied at the free end is 2 kilonewton. So the produced deflection, let's say B. Now the same beam I'm taking here, but the load which I'm applying here is 3 kilonewton. Now the superposition principle says that the C deflection is equal to sum of deflection A and B. So this is the representation the system behaves elastically. Coming to nonlinear analysis. So in general, we are not usually suggested to design any structure for an elastic criteria, because all the structures will behave nonlinear only. It attains the material nonlinearity. So loads are beyond the elastic range of deformation here, and the superposition principle is not applicable. So here we can able to see this graph. The stress, this load deformation is proportional up to some point, and then the nonlinearity is started. And also the load is equal. Load is equal to stiffness multiplied by displacement. So load is this stiffness is the function of displacement. Now coming to this classification of analysis based on the deformation. Here two categories are there. One is a small deformation analysis. Another one is a large deformation analysis. In small deformation analysis means I'm going to consider only the preliminary effect. What would be the preliminary effect? I have a beam, load is applied, started deflecting. So that is the preliminary effect. So material nonlinearity only I'm going to consider. If it is a large deformation, then I have to consider P delta analysis. So those who are designing or analyzing any structure by using a StatPro, ETABS, SAP, or any other design softwares, they are going to see one checkbox in the StatPro that whether we are going to consider the P delta analysis or not. So let's discuss what is P delta analysis and how it is contribute to the material nonlinearity. So I have a column. At the top of the column, there is a point load. So this point load is exactly at the line of axis. Now this column is subjected to some lateral load. What will happen? The column will be displaced in this position, but still the load is acting here. So this load multiplied by this horizontal distance will create the secondary moment, that is the P delta analysis. So when the secondary moment is possible, the column is not at all vertical position. The column is displaced. So this distance, that horizontal distance, going to create the secondary moment, which should be considered in the analysis and design. So that's why we have that option in all the design softwares. So this terminology already I have explained. Degree of, but in more detail we'll discuss here. Degree of freedom in structural dynamics or kinematic indeterminacy in structural analysis, both are same. That means the number of independent coordinates required to specify the motion of the system. For example, in the structural analysis, if you consider the fixed beam, it cannot move in any direction. Both the support conditions are fixed. So the number of displacement coordinate for the fixed beam is 0. Let's see, we have a mathematical model of single degree of freedom. The mass is lumped. So it is only subjected to the lateral displacement. If you any direction you supply the lateral displacement also, lateral push, the displacement will be same. So it is considered as a single degree of freedom system because it's going to give only one displacement. Now let's take a ship. Ship is having 6 degree of freedom system. That means 6 possible way it can able to rotate or move. So 3 are the translational degree of freedom and 3 are the rotational degree of freedom. For example, ship is moving in a forward direction. That translation motion is called as a surge. The same ship is moving in a transverse direction, that is called as a sway, and the ship is moving in a vertical direction, that is called as a heave. Now coming to this rotational degree of freedom. If the ship is rotating in a x-axis, that is called as a roll, and the ship is rotating in a y-axis, that is called as a pitch, and the ship is rotating in a y-axis, that is called as a yaw. The same thing is applicable for aircraft also. The ship is having 6 degree of freedom, aircraft also having 6 degree of freedom. That's why the design concept of aircrafts are complex in nature. So we are now at the vibration of single degree of freedom system, what you are seeing here is a multi-story building. So you see every roof level, we are lumping the mass and then mentioning for first floor, stiffness 1, K1. For second floor, stiffness 2, K2. For third floor, stiffness 3, K3. Like that, we are having the corresponding masses also. But before discussing the multi-story building system, we'll discuss the single degree of freedom system for better understanding. So what I'm doing, I'm taking the first ground floor only, okay, and then converting that into the lumped mass system. Now, if you convert that into the lumped mass system, this is the free body diagram or mathematical model. Here we can able to see two columns are there. Actually, many columns will be there. It represented as a two columns, and then the corresponding stiffness is marked here. Then the arrangement which you are seeing here is called as a damper. Generally, different types of dampers are there. Viscous damping is there, structural damping is there, fluid damping is there, many radiation damping is there. So generally, in the structure, the damping force is represented as a fluid viscous dampers. Okay, so this container is called as a dashpot. Dashpot means it is a mechanical device in which they are filling the oil or a highly viscous fluid, which is going to control the displacement. Now, I'm taking the cross section of the mathematical model. You see in right hand side, the P of T is there. P of D is the externally applied force, which is dynamic in nature. And what are the internal forces are there? Spring force is there. And then FD damping force is there. Once the externally applied force acting in a right hand side direction, then the inertia force will act in the opposite direction. That is called as a D'Alem's principle. Moving mass generates the inertial force, which is opposing the motion of the structure. Now, we know Newton's second law of motion, which is force is equal to mass into acceleration. So we wrote that equation. Right hand side, we can able to see m u double dot. U represents displacement. U double dot represents acceleration. So mass into acceleration equal to all the forces in left hand side. P is the external force and Fs is the spring force, which is nothing but the coming from the columns, and then Fd is the damping force. So this is the equation of motion, which is nothing but mu double dot plus cu dot plus ku is equal to P of t. So equation of motion comprises of four components. One is mu double dot is the inertia force, cu dot is the damping force, and ku is the spring force or stiffness force. And P of t is the externally applied force. So whatever we discussed, this equation of motion is for elastic system. If the system behaves inelastically, you observe here the stiffness in the equation of motion, see the Ku term, the stiffness is only the function of displacement here. If the system is inelastic, then the stiffness is the function of velocity also. Displacement as well as the velocity. So that is the difference between the linear system and then nonlinear system. So taking the same mathematical model, but this time it is called as a spring mass damper system. So this is a kind of free body diagram. By using that, I can able to derive the equation of motion. So I made a block inside that. When it is moving, it generates the inertial force, moving mass opposing the direction. So you see here mu double dot acting in a left hand side direction, mu double dot in a left hand side direction, and P of t is in a right hand side direction. So what this external force is doing, pushing the system in a right hand side direction. So opposite to that, the inertial force will be generated. Similarly, the column going to resist, the damping force going to resist. What is mean by damping force? Damping is a force which acts opposite to velocity of motion always. Always damping force will act opposite to velocity of motion. So once again, the equation of motion, this is the equation of motion for damped forced vibration. Now, this is just an equation of motion. It is not a solution. What is the solution? We need a response of the structure. That response is nothing but the displacement. The displacement is within the limit. The structure is safe. The displacement is exceeds the limit. There is a possibility of formation of plastic hinges so that the structural integrity will be get affected. So for solving this equation in dynamics, we have many methods for solution. These are the four methods. One is a classical method of solution. Another one is a Duhamel's integral solution, transform method, and numerical method. We'll see one by one. Classical method of solution is a pure mathematics. It comprises of complementary function and then particular integral. So the system is not having any externally applied force. Then the complementary solution alone is enough to solve the problem. If the system having the externally applied force also, then the particular integral also will come into the picture. So if you see the complementary solution here in the slide, free vibration component and then transient components are considered. You see the particular integral, forced vibration component and steady state components are considered. So the total solution u of t is nothing but the displacement varying with respect to time. U c of t is a complementary function and u p of t is the particular integral. Now, Duhamel's integral is another method to solve the dynamic equilibrium equation or the equation of motion. Whatever you are seeing is a load time history. So load is P of t in y-axis and the x-axis we have a time scale. So automatically you see this load is random in nature because it's not a sine load or a cosine load. It's random in nature. What they will do in the second diagram you see in the load itself, load graph itself, they are going to consider 1 unit of impulse. Integrating that 1 unit impulse to 1 impulse and then integrating along the time frame, we are going to get the total response. And the next method is transform method. Two transform methods are there. One is a Laplace transform method. Another one is a Fourier transform method. What it will do exactly, it will convert the dynamic differential equation. It will convert the differential equations into the algebraic equations. For example, Runge-Kutta method, Picard's method. These are the numerical methods easy to solve. That's why, but the differential equations are very difficult to solve. That's why if you use these two methods, it's easy to simplify the problem. Now coming to the numerical method, which is our topic actually. You see all the three methods I have explained previously. That is a classical method, Duhamel's integral method, and then transform method. In that these two methods are there, Laplace transform and Fourier transform. All these three methods are applicable only for the elastic system. But in reality, all the structures going to behave non-linear, particularly it is subjected to the earthquake loading. So that is the reason we have to go for a numerical analysis. This numerical method is incorporated in the simulation packages. We are going to get the accurate results. If you talk about the vibration of system, it is classified broadly, which we are going to see now. So this vibration of system, we have a free vibration. Free vibration in the sense we have a cantilever beam. There is no loading condition. Simply I'm applying the initial displacement and then removing. Once you apply the initial displacement and remove it, it is going to vibrate. But after some times it will come to the condition because there is no damping in it. So that is the free vibration. And there is no forcing function also. So in this free vibration, further we are going to have damped free vibration. Damped free vibration means the damper is installed in this beam. If the damper is present here, applying the initial displacement, then it is going to vibrate. After that, it will come to the rest because of the damping present in the system. What is damping? It is a force acting against the or opposite to the motion. Okay. So, and then damped system is there, undamped system is there. If you come to forced vibration, there also damped forced vibration is there, undamped forced vibration there. So what is the forced vibration? Load will be there at the free end, continuously pushing the system up and down. Okay, that is a forced vibration. Damping also will be there. That is the damped forced vibration. Forcing function is there, but damping is not there. That is the undamped forced vibration. So this is the all classification of vibration system. There is no vibrations more than this. So once again, taking the dynamic equilibrium equation for undamped free vibration. So mu double dot is a inertia force, Ku is the spring force or stiffness force, equal to 0 because I made P of t is 0 and Cu of t Cu dot also 0. Now we'll see how to derive the solution for this. So here if you see, we are assuming the trial solution U is equal to e power st. This e power st is generally considered for simple harmonic motion. So I consider the trial solution differentiating. So I will be getting a u dot, which is s into e power st. And then differentiating once again, I'm going to get s square e power st. Substituting both these in the dynamic equation, we'll be getting this. In this equation, I'm taking e power st commonly outside. So here two components we can see. One is m s square plus k and e power st. Either ms square plus k will be 0 or e power st can be 0. But in this case, e power st cannot be 0 because that is the assumed solution. If you make e power st is 0, then it is going to give you the trivial solution. So obviously, ms square plus k is equal to 0. So if you solve this equation further, I'll come this side. Yeah. If you solve this equation further, we are going to have two roots. For the two roots, we'll be getting the natural frequency omega n, which is square root of k by m. And then further, we want to eliminate the constant so that this is the complementary function actually. So this is the complementary function and we are incorporating all the mathematical terms here. Then we will be having the u of t. U of t is nothing but the displacement. So here you see there is two constants are there. One is C1, another one is C2. We need to eliminate this constant. For that, I'm applying the initial condition. When time t is 0, the initial displacement is 0. If the initial displacement is 0, the velocity also 0. So that is our initial condition. T is equal to 0 means initial displacement is 0, velocity is 0. And then we substituting this equation, we will be getting the constant C1 and C2, substituting back to the equation. And this is the solution for u of t means is the displacement which vary with respect to time for a undamped free vibration. Now we'll plot this and then we'll check how it is looks like. And so this is the undamped free vibration. If it is a damped free vibration, then we are going to have the exponentially decaying function e power minus zeta into omega nt. So that is the parameter removing the vibration energy from the system. Okay, and then we can able to see another terminology also. Omega d is the damped natural frequency. So this is a damped natural frequency. And zeta is the damping ratio. So zeta comprises of C and CR. The damping present in the system where CR is the damping energy required to remove the vibration completely from the system. So undamped free vibration equation. This is the undamped free vibration equation. If you plot this, it will be like this. Here, the x of 0 is there. No, this x of 0 is nothing but the cantilever beam is there. I'm applying the initial displacement. That initial displacement is x sub 0. What I will do, I will apply the initial displacement and then remove it. Then the system is start vibrating. So that vibration is plotted here. Now you see, this vibration is always there. It is not coming to the rest because the reason is the damping force is absent here. But in reality, such kind of structures are not there. Only we used for theoretical applications. Now coming to the next case, this is the solution for damped free vibration. If you plot this, same wave pattern we are having and e power minus beta into omega nt is there. Now you see the response, this response and this response. This response is exponentially decaying. That means what? After some time interval, this response will come to the end and the structure will become stable completely in the rest position. So that is the reason in the multi-story buildings, they are using the dampers. So in this cylinder, they are going to fill the high viscous fluid, which is connected to the floor and then roof level. So during the earthquake, what will happen? This floor will be pushed in this direction, roof will be pushed in this direction. So it is going to control the displacement. So in the summary, what we have studied here, we studied the various classification of analysis in the structural dynamics. We are studied how to derive the dynamic equilibrium equation or equation of motion, and then what are the various solution procedures are available to derive the solution for the equation of motion. And also we studied what is mean by damping and the various vibration categories. So in my lecture, I want to include these basics of structural dynamics because these mathematics, these concepts are related to my research topic. So now only I'm going to discuss about the offshore structures. So this structure is subjected to the vibration because of multiple loads, which is dynamic in nature. So the picture you are seeing is the real offshore structures, which is there in the Gulf of Mexico. These offshore structures is generally used for drilling, production, and processing of oil and gases, which is comprises of uh, two parts, namely the superstructure and then substructure. Superstructures are nothing but it is similar to the industrial structures. Okay, so there they can use some storage compartment, lot of machineries will be there, the tower crane will be there. So a lot of operation will be happening here. But in offshore structures, they are going to store hydrocarbon and all. So which is vulnerable to explosion. Coming to the substructures are made of pontoons. That means what? It is going to give the buoyancy force, and by using the tethers, this structure is anchored into the seabed. So one may ask, we can go for a foundation in the seabed and then we'll construct the structure. But whatever the oil reserves are available, that is deep into the ocean. So constructing the structure with the foundation, it's not economical. That is the reason we are going for a floating structure. So these tendons or wire ropes are anchored in the seabed so that the structure is stable. They are going to perform the drilling operation and then also the protection and processing of oil also can be done here only. So this top side comprises of heavy machine force, multi-tier decks, which is supports this drilling and protection operations. And inside this three decks, all these components are incorporated here. You see the protection separator, pulleys, electrostatics, desalter, various compartment which supports the production and processing of oil are installed in this topside. It is offshore structure. Superstructure is all called as a topside. Okay, so this offshore structure is highly vulnerable to hydrocarbon fire, explosion, impact load, wave load, wind load, and fire. That is the reason these structures are complex and we need to analyze properly by using the proper material and then design. So as I said, the topside is vulnerable to the special loads. Generally, the word we are using special load that includes. Okay, we'll take a 5 minutes break and then we'll continue. Okay, dear participant, there is a technical problem here. There is a delay between my voice and the slide which I'm showing there. I hope this issue was there. We try to fix this issue. If this issue continues, once again, please you can text in the chat box or in the WhatsApp that online lecture series group so that we'll pause it and fix this issue once again. I hope now what you are seeing is a introduction to the offshore structures, and there is no delay between my voice and the PPT which you are seeing now. So once I'm skipping the PPT and going to the next slides, please confirm it. So here we are. The offshore structures comprises of multiple unit, which makes offshore structures more vulnerable. So here, the special load terminology includes the base load, fire load, which are unconventional loads compared to the conventional structures. And also, the probability of occurrence of special loads in offshore structures is very, very high because of that so many modules and component it comprises. In addition to that, if you see the offshore platform or offshore structures, it's not like a conventional structures. For example, the column to column spacing in general practice, you should not be more than 4 meters, but in offshore structures, it is very, very large. And also the one floor height will be equivalent to the in commercial or residential building, 3 floor is equal to 1 story height. That is also what will happen. The columns are subjected to buckling, and then beams are going to undergo excess deflection or flexural failure. So I have changed the slide here. The next slide, what you are seeing here, the top side requires high strength material to resist stresses and fire load. So why we need to do this research, the extensive research on material and dynamics and all, because whatever the material they are using for offshore structures in the regular practice, those metals only not sufficient for the durable structures. So we look for the material which can resist the higher pressure, higher temperature, which is going to give the higher resistance to the corrosion, which offers the good weldability. All these parameters we need in a single material. That is the reason we go for a functional graded material. That's why it is called as a novel material. So preliminarily, I'm going to show the top side. That means the offshore structure is modeled by using the FGM and X52 steel. And also I performed the wind, the top side is subjected to the wind load, impact load, hydrocarbon fire and explosion. And I performed also the free vibration analysis. All these load together acting in the structure, then what is the consequences? That is also we are going to discuss. After that, I will go for a research scopes. Now, I hope the slide which you are seeing is a functional graded material. Okay. So since I told the one material serves multiple purposes, for example, good weldability, high resistance to the corrosion, higher resistance to the temperature, pressure, how we attain this? We can attain this by superimposing, or we can attain this by fabricating the single metal piece by using different superior materials. So I'm going to show the videos and all. It's easy to understand. Please follow up. So the functional graded material exhibits a continuous variation of material properties which results from non-homogeneous microstructure. These materials can be fabricated by two methods. One is continuous method, and the second diagram shows the stepwise method. In continuous method means the metal is made into the powder, and by using the centrifuge action and extreme temperature, the material molecules will be penetrating the another material molecules, and then this kind of smooth structure will be getting. But the second method is a stepwise method. In that, whatever the steps you are seeing here, the different blocks, all are different materials. The one may ask, this may get delaminated. So this is not a composite structure. Even though the metal having a different material composition, it will act as a homogeneous material. So that is the peculiarity of this FGM. So this may be a carbon manganese steel, this may be the titanium, and this may be the nickel, and this may be some other material. So what is the various advantage of using FGM? First of all, it is going to give the better resistance to bending, buckling, and extreme temperature, improved residual stress distribution, enhanced mechanical properties, higher resistance to fracture, and then buckling. So this is the video I'm going to play how the functional graded material is fabricated. So wire arc additive manufacturing method, that is called as a WAM. What does that means? The welding arc is attached on the 3D printing machine. So nowadays the 3D printing machines are very famous. Whatever the therein we are our mind, we are going to fabricate it. So what here they are doing? Let me pause this video. What exactly they are doing? Wire arc is attached to the 3D printing machine, and this arc is going to have the controlled electricity, controlled fuel, and then the metal supply is given as the wire. So if you want a titanium, we are going to attach the titanium wire and some other different materials. And then we are going to fabricate one layer of material, replace the material, another layer of material, another layer of material. It will be functionally graded. So they are making a pipe bend by using the wire arc additive manufacturing method, WAM. So whatever you are seeing here, this is the functionally graded material. When I was doing my PhD in IIT Madras, this wire arc additive manufacturing method is facility is available in the metallurgy lab. So what I have taken, I have taken two material samples here. One is a duplex stainless steel, another one is a carbon manganese steel. So this carbon manganese steel offers very good weldability, and the duplex stainless steel offers higher resistance to pressure and temperature. So the melting point of the duplex stainless steel is around 1300 degrees Celsius to 1400 degrees Celsius. So by combining these two metal, I got these properties. You see the third column, FGM, which is compared to X53 steel. This X52 steel is also one of the superior material which is more prevalently used in the offshore structures. But in order to show the superiority of the FGM material, I am comparing with X52 steel. So you can able to see the yield strength is enhanced yield strength is having, ultimate strength is 588, strength ratio, ductility ratio, toughness, all parameters are very high compared to even the high performance material. So I have casted three samples. The first sample is tabulated here, which is comprises of duplex stainless steel and then carbon manganese steel. The second sample, which I have fabricated, is comprises of duplex stainless steel, pure nickel, and then carbon manganese steel. And the third sample is comprises of duplex stainless steel, carbon manganese steel, pure nickel, and then titanium. So here nickel is used as a buffer material, because when you are fabricating one material over another material, sometimes it won't stick. It won't get any bonding. In order to make that bonding, we are introducing the buffer material, that is the nickel. So here, using the wire arc additive manufacturing method, the sample was casted. Here we can able to clearly see bottom, this is the carbon manganese steel, and then this is the duplex stainless steel. So obviously, which we are going to put it in the UTM and we are going to test the tensile strength. And here we can able to see some diagrams. For example, the tubular section, the inner wall is made of one material and another wall thickness is made of another material in order to satisfy the functional requirements. Similarly, we can cast any sections circular in nature or even the structural cross sections like I section, channel sections, etc. So with these, based on the functional requirement, we can choose the different materials fabricating by using a wire arc additive manufacturing method, and then we can see and compare the its performance. once you get a higher performance, that material can be used for the complex structures. So what I have done, I modeled or designed this offshore structure topside by considering the X52 steel, because that is one of the high performance steel I consider. Due only in the vulnerable regions where the hydrocarbon fire is possible, that location only I used FGM, because fabricating FGM at the laboratory level may be easy, but for the construction of the offshore structure, we need to fabricate the huge cross sections, which is practically uh, difficult. So initially, while we are designing the structure, we can able to see the red color and yellow color and all. It's not having the adequate strength. It's failing actually. So after optimizing the section, we'll be getting all the structural members are passed in the design check, and then this is the optimized cross section of the members. Generally, if you see the offshore structures or steel structures, they will go for a tubular section, because tubular section, light in weight, going to give the very good moment of inertia. Moment of inertia is a capacity to resist bending. So, and then the top side or offshore structure is examined under the action of wind load. So what I have done here, the wind loads are calculated based on the gust factor method as per the IS codes. Since this topside is located in the Gulf of Mexico, it's a real structure, it is located over there. There the wind velocity is 55.88 meter per second, which was incorporated in the equations. Now we can able to see here, at every level of the deck, the horizontal force because of the wind is calculated. Okay. And then once this load is calculated, we are going to apply on the topside structure. Then the offshore structure, the topside structure is evaluated under the action of blast load. The response is analyzed under the action of blast load. So beam column connection of the topside analyzed under the blast load caused by the hydrocarbon explosion by using the abacus. So we know abacus is one of the finite element package that we can able to do the simulation of any steel structures, concrete structures, etc. It is one of the finite element tool. Okay, so it is one of the finite element tool. So here the blast pressure is converted into the linearized triangular impulse to simplify the problem, which we can able to see it in the graph. And then this blast overpressure is applied on the surfaces of the beams and columns. So in Abacus, we can able to incorporate the temperature data also. But generally, the peoples who are willing to do the analysis of structure, any structure under the action of hydrocarbon fire and explosion, you have to go for LS Dyna. So you know that fire is the chemical process. Just a minute. Any issues? In presentation mode itself, you need to zoom. Okay, sorry for the interruption. We'll continue. Zoom it. Is it okay? Okay, fine. Okay, sorry for the interruption. There is a technical issue here. Okay, then this blast over pressure is applied on the beams and column surfaces. And the dimensions of these beams columns are chosen based on the existing offshore structures already. And then the analysis was made and the response is compared with the FGM and X52 steel. So people, those who are doing the numerical simulations, we would have heard the term like mesh convergence analysis. So in finite element method, what we are doing, we are discretizing the structure into finite, infinite elements, infinitesimally short blocks. And we are plotting the stress, strain, plastic strain, all those plots. So if the mesh size is very less, we are going to get more accurate result. But there is a problem with that. When you are optimizing the mesh, for example, here the mesh size is started with 100 and optimized with up to 54 Once you keep on decreasing the mesh size, the analysis will become tedious. It is going to be a time consuming process. So here, instead of 54 the mesh size we can able to take 1 also, but the analysis itself will take 2 months. So 2 months your computer should be completely on, the electricity should be given to the computer. So here you can able to see the block was there. This is the model of block, one of the module in the offshore topside structure. There the beam column connection is taken, the configuration is taken, which was modeled in the abacus. Then we performed the analysis and plotted the plastic strain. Here we can able to see the green color one and then blue color one. So green color is the material FGM. Plastic strain is very less compared to the another superior material X52 steel. What is mean by plastic strain? The permanent deformation. So if there is a permanent deformation in the structure, it will create the plastic hinge. Plastic hinge means it is a zone of yielding in the structural member because of the flexural action. So we never want a plastic strain. We never want the permanent deformation. We never want the plastic hinge. Then only the structure is having the sufficient strength. So here we can able to see, even though compared to the superior material, the FGM showed enhanced or reduced the plastic strain of 29%. Similarly, the beam displacement, column displacements also evaluated, which shows 18% and to 20% the differences performance. And then what you are seeing is a von Mises stress plot. So we know von Mises stresses is one of the failure stresses. So when you are performing any analysis, the von Mises, the failure stresses should be very less. So here we can able to see the structural members, that is a beam column connection made of FGM undergone very less amount of von Mises stresses. So here we can able to see the differences in the tabular column, the table FGM and X52 steel, and the last row is differences. Please see that differences, the third row, 29% reduction of plastic strain, and the displacement is reduced to 18%, and column displacement are reduced to 19%. Similarly, there is a reduction of von Mises stresses also. So the functional graded materials are used in many fields generally, particularly in aerospace, the fighter aircrafts and missiles, and also energy, nuclear power plants, thermal power plants, and biomedical engineering. But the use of functional graded material as a structural member last 5 to 6 years only it was developing. And people who are the researchers, they are by using the wire arc additive manufacturing method, they are developing different material composition to enhance the performance. So FGM can be an alternative construction material for offshore topside, not only offshore topside, any industrial buildings also, which is vulnerable to the dynamic loads. But here the problem is we cannot go for 5 material, 6 material composition. Fabrication process itself, it's very difficult. And if you want to execute the same thing for a real life structure, we need to fabricate all the structural components, which is very difficult. So it is advisable go with 3 to 4 materials maximum. So then that offshore topside structure, is analyzed under the action of impact load also. Generally, these offshore structures are vulnerable to the missile attacks because it is offshore structures is only responsible for the protection of crude oil. So in onshore also the crude oil wells will be deployed, but the reserve is more in the deep inside the ocean. That's why we went to the offshore. So these structures are highly vulnerable to the missile impact. Apart from that, these structures are having the cranes, which is always lifting some heavy modules and keep it in the position. And this fall of modules also going to cause the severe damage to the offshore structures, which is going to affect the performance or even the shutdown of the offshore structure for 2 to 3 days. So here the FGMs are used to model the deck plate and the stiffeners to improve the strength and compared with X52 steel and then aluminium. Here I have taken the aluminium also one of the material. Interestingly, the reason is aircrafts are made of aluminium. The warship decks are made of aluminium. So it should not penetratable by any missile attacks. So what you are seeing is offshore structures here. At the rooftop is indicated in the red color thing because it is going to have the drilling module, crane, derrick, all those things. So it is, and in addition to that, it is susceptible to or subjected to the missile impact. So that the dimensions are tabulated over there. If you download any papers related to the offshore structures, there is a limited amount of dimensions related to the offshore structures because these are done by the high-end consultancy works and generally they won't share it in the any medium. So this is the plan view of the top side. In that, the small portion is taken for the analysis because there the explosive materials are stored, for example, hydrocarbon or crude oil. And then the deck plate is supported by the stiffeners in order to resist the penetration of the missiles or the fall of objects. For reality or practical application, what I have done, I have taken the crane hook, which weighs 2.85 tons and falling from 20-meter height was considered and directly on the deck plate. Then what would be the consequences? It was analyzed by using abacus. So here you see the deck plate made of two different material. One is a duplex stainless steel. We know that duplex stainless steel offers higher resistance to penetration and it is going to have higher resistance to corrosion. And the bottom material is a carbon manganese steel, which offers very good weldability. So these numerical analyses were performed. Stiffeners are attached to the bottom of the deck plate and the boundary condition, all the direction of the deck plate is attached with the fixed boundary condition. Here also mesh convergence analysis is done to get the appropriate results. It was optimized from 100 mm to 36 mm. So still we can able to reduce the mesh size, but we need the higher end laptop or PC to perform that analysis. So here we can, what you are seeing is a impact strength. So contact force is the resistance against the impact load. So once the projectile or the crane who come and hit the deck plate, what will happen? Immediately the resistance will be get increased. And then we can able to see the decrease in resistance. This is because the projectile coming and hitting the surface and then it is bouncing back. Okay, so it was plotted here. We can able to see the functional graded material offers higher resistance followed by X52 steel and finally the aluminium. But we cannot able to use the FGM or X52 steel for the entire part of the aircraft or any important structure because it's more weight. Aluminium only, the strength to weight ratio is very, very high. That means very less weight, but offering higher strength. That is why the aircraft are made of aluminium. Then contact forces versus impacted displacement you see here also we can able to observe the same phenomena. Functional graded material offers higher resistance under the impact load. So In the results, we can able to observe the impact strength of 19% and 40 when it is compared to X52 steel, 19% enhanced strength we got, resistance we got, and 47% compared to aluminum. So similarly, the deflections also are plotted here. So we can able to see the enhanced performance and then the plastic strain. So these are the parameters: plastic strain, displacement, contact force, and then one messy stresses are very, very important parameters when the material subjected to non-linearity. So here we can able to see the one messy stresses. First one, this graph is kinetic energy. So when the projectile come and hit on the surface, the plate going to absorb some energy. Okay, the plate made of functional graded material possesses higher amount of the kinetic energy compared to remaining two materials. So energy absorption is very, very important. If any material completely acting as a rigid material, not absorbing any energy, the collision impact will be very, very high. So it should generally deform in the elastic manner. It should not attain the permanent deformation, which is going to affect the platform operation. At the same time, it should dissipate the energy. Okay, so that's why these materials are taken for the analysis. Similarly, we can able to see the second plot is the one messy stresses. There also the failure stresses are very, very less. The green color plot, you can able to see that the failure stresses are very, very less. So here the one messy stress contour, which you are seeing for a different materials. The stress concentration in FGM is less compared to other materials. And this is the response of deck under impact load. Here we can able to see the first row is the FGM, X52 steel, aluminum. FGM is compared with X52 steel. FGM is compared with aluminum. So when we are comparing with aluminum, nearly 50% enhanced results we are getting. When we are comparing with X52 steel, nearly 10 to 8% enhanced results we are getting. So here the research scope is whatever the results I got, that is for a specific combination of FGM. If you go for the different application, if you cast it for the different materials, definitely we are going to get the higher performance than this. So what I have done so far, we discussed the offshore structures subjected to wind load. It is subjected to the blast load. It is subjected to the impact load. Now, if all the loads together acting on the structure, what it is the consequence? What would be the consequence? So all the loads are applied to the structure. Whatever the red color members you are seeing, initially it was failed because of the combination of loading condition. To further enhance the performance, all the beams and failed columns are replaced here with the functional graded material. Okay, and then I have performed the pushover analysis. Pushover analysis in the sense we are pushing the structure horizontally until it fails. So once the lateral load is applied to the any structure, what would be the consequence? It is first of all, it is going to attract the secondary moment and then huge displacement. Because of this secondary moment and the huge displacement, plastic hinges will form in that structure. So in the plastic hinge also, the various range of plastic hinges are there. For example, the earthquake is very, very minor. In Richter scale, it is a 3 only. Even though ground acceleration is happened, the structure is subjected to the shaking, oscillation. Because of that, whatever the plastic hinges are formed, that would be at the level of life safety or collapse prevention. It is not a collapse. But in the pushover analysis, we are pushing the structure until collapse so that we are going to get the complete collapse pattern in the pushover analysis. That's why we are performing. So here we can able to see the last plot. The base shear is we are getting more base shear while using the functional graded material. This is because the functional graded material offers higher stiffness. Now, the collapse pattern in the case 1 is only using the X52 steel. Case 2 is using X52 steel and FGM. And the results are compared here. So in case 1, we can able to see the range of plastic hinges, immediate occupancy, and then life safety. In case 2, it is immediate occupancy hinges are there, life safety hinges are there, collapse prevention and collapse hinges also is there. Okay, so that is the difference. Then I took a structural member and performed the free vibration analysis. So why we need to perform the free vibration analysis means the free vibration is the natural property of the system, that to the first mode. When the natural frequency matches with the forcing frequency, it will cause the resonance. For example, the cantilever beam is there. It is going to have some natural frequency. It may be omega n is equal to 10 radians per second. Now I'm applying the dynamically varying load, or I'm installing a rotating motor over there, which is going to produce the vibration. That is the forcing function. Now, this forcing frequency and this natural frequency will matches. It is going to create the resonance condition. In resonance condition, the member displacement will increasing exponentially and failure will happen. To avoid, one must know the natural property of the system, which is nothing but the natural frequency, so that we can able to predict the collapse pattern of the structure. So here the cantilever beam was taken, which is having a tubular section, comprises of two metals made of FGM, and that is the abacus model. So what you are seeing here is the displacement profile. I told the FGM possesses higher stiffness. In all the graphs, we can able to see the FGM displacement is lesser compared to the X52 steel. So this was analyzed for all the modes. Okay, modes means mode shape. Mode shape represents the collapse pattern of the structure. Here you see in the first mode, the displacement is translation. Okay, it is displacing only in the one axis. In the second mode also, the displacement is not complex. Third mode also, displacement is not complex. But if you observe the fourth mode, it is the torsional mode. Torsional mode means what? The cantilever beam is there. It is not only deflecting in the XY axis, it is also twisted. The warping takes place. Similarly, we can able to see the fifth mode, sixth mode, seventh and eighth mode respectively. There will be the lot of antinodes. Finally, you can see the 10th mode. The vibration is highly, very extreme. So wherever we are getting the peak vibration in the beam, that location we need to add more stiffeners to arrest that vibration. So we know which part having more amount of displacement. In that part, we are going to increase the stiffness by attaching the steel plate on both the sides of the beam, soffit and top of the beam also, so that the stiffness will be increased in that particular place. We are going to avoid this red color peak. So we can able to see the green color represents the functional graded material natural frequency. Red color indicates the X52 steel natural frequency. So natural frequency is higher in almost 0 to 10th mode. By using the functional graded material represent FGM possesses higher stiffness. So it is a suitable candidate for the offshore structures. And these are the findings from that free vibration analysis. It offers more rigid and have a greater resilience to vibration in higher modes, and also better against torsional modes, lesser warping in all modes, and lesser antinodes in higher modes, and also enhanced natural frequency of 15% indicates enhanced stiffness. So, however, analyzing the beam under forced vibration condition may attract the researcher to explore more about the FGM. So this is the one of the research scope. The reason is The combination which we are used here is completely the new material. The same combination, if you do the forced vibration analysis also, it is one of the novelty of the work. This is the overall conclusion of this presentation. The preliminary design which we made fulfills the design codes, not only the Indian codes, multiple code books are used here, Euro code, American codes, etc. And the top side is safe against the wind load and all the payloads and all the combination of special loads, which is wind, blast, impact load, etc. With all these load also, we've attained reduced plastic strain, reduced beam tip displacement, less concentration of failure stresses, improved strength, and reduced plastic strain and central deflection. And this is the conclusion derived from the pushover analysis. When we use the two materials, X52 steel and FGM combination, we don't have any collapse hinges. But when we use the X52 steel alone, there is a collapse hinges also, which is not good for the integrity of the structure. So here, what the conclusion is, FGM enhances the mechanical property, plays a crucial role in maintaining the topside integrity and avoid collapse hinge formations. And if you take any research work in the first seminar, they are going to ask what is the novelty of this work. So novelty can be obtained in different ways. One of the thing is, if it is experimental work, we'll be going for a new methodology or new combination. For example, here, a few of the novelty of my works are this topside under critical load combination. First of all, is a conventional practice. But if you go for a special loads, that to the combination, that itself one of the novelty. And then the secondary thing is the FGM composition used for this research work is offers higher resistance to pressure, temperature, offers good weldability, offers higher resistance to corrosion. That is one of the novelty. And then the another thing is the designers. It's going to help the designers easy to understand the behavior of the FGM, and this they can easily use it to the design. So these are the research scopes which will be the take home. First of all, the impactor rotation angle. For example, the plate is there, the projectile is coming. It is not going to be in the only stationary position. It will be going to have the eccentricity. It is going to be rotate also. So that rotation angle we should consider in that many categories there, which is one of the research scope. And then the plate is there, missile is coming. We cannot ensure that the missile is exactly going to hit on the center of the plate. It may hit anywhere on the top side structure. So if you consider the various eccentricity and the rotation angle, that is one of the research scope. And we can consider various masses and velocity of the impactor also, because nowadays day-to-day activity we are while seeing the news also, we used to see the Israel and Hamas war. They are using the different missiles, which is more costlier, more advanced one, which can able to penetrate the concrete depth of 1 meter also. So the material which we are using, it should possesses the adequate strength, so that it is very important to consider different masses based on the missile weight and then that impact force. And also, if you produce the design aids for the functional graded material, they no need to analyze while they are designing the offshore structure. Simply they are going to see, okay, for this cross section, this is the maximum deflection, this is the maximum load it can resist, and this is the one Messi stresses failure criteria. Directly they are going to pick that section. So that is, if you produce the design aids, nomographs, that is also one of the design research scope. And finally, offshore structures are vulnerable to the hydrocarbon explosion. If the explosion happens, what will happen? Suddenly the columns and beams will be terminated in the particular location. So obviously, whatever the loads were taken by those columns will be transferred to the supporting columns, which is going to initiate the progressive collapse. So progressive collapse of the industrial structure or offshore structures also one of the research scope. Apart from this, there are many other research scopes are there. You are free to contact me since my mail ID is shared with you. So I can able to share many research scopes related to this field. And these are the research outputs made from these concepts, references. I thank you for listening to this lecture. I appreciate for this opportunity to speak with you regarding this topic today. Now it's a question and answer session. So those who are having any doubts, you are free to ask now. Any questions? Dear participants, any questions are there? So I look into the chat box. So I am in the chat box. If there is any questions, you can ask. Okay, since there is no question, we'll close this session. Okay, one more request from my side. Kindly share the feedback on this lecture. The link will be shared in the online lecture series group. And there is also the quiz based on these topics. Kindly participate in this quiz. Definitely will help you to enhance your knowledge related to this field, so that I can able to observe how much you understand this lecture based on your performance in this quiz. Thank you.